Again, everyone, this is chapter 5.3, properties of logarithms, and I'm going to first start by showing you the biggest three properties of logarithms that there are and that will be seen in this section. There's actually one more thing we have to see besides just these three properties, but I need to show you at least a power rule to show you that property, just to convince you that it's true. So here I'm going to show what these properties are and prove them as well, and then we'll see some examples in the next screen. But in any event, let me fill in the blanks here. So for here, the product rule, log base b of a product x times y is the sum log base b of x plus log base b of y. And the real reason why this is true is essentially why it's true for exponents. So if you think of what happens when you have a base to a power times a base to another power, you add the powers. And since logs are powers, remember logs solve for powers, this basically says the power of one base plus the power of the other base is, well, the product of each of those bases to that power. And I'll show you that in the proof, but first let me fill in the rest. Quotient rule says very much similar thing here. It says log base b of x over y is log base b of x, the top one, minus log base b of y. And I don't think that's too much a surprise for anyone, because just as multiplication corresponds to addition and division will correspond to subtraction. Okay, now what about for when you have a power? So this is the power rule. So log base b of x to the r in this case. This says that r comes down and is multiplied by log base b of x. So basically you can bring the power out as a multiplier. Very, very, very useful rule. In fact, I love the power rule the most out of all of these. I'm going to start with this. And it's kind of used all the time. The power rule is great. So now I'm going to prove each of these, but before I prove them, let me try to establish some language in the proof. I'm going to let m be log base b of x, and I'm going to let n be log base b of y. So with that being said, converting these to exponential form will give me the base b to the power m is equal to x. And here converting this to exponential, so I guess I should write that label in for the arrow. This base b to that power n is equal to y. And now we're going to see the proof of the product rule first. So to prove the product rule, well, we want to find log base b of x times y. So if we multiply x and y, well, what's x and y multiplied? X and y multiplied is b to the m times b to the n. But again, like I said earlier, when you have a multiplication of two powers of the same base, then this is just the base to the sum of those two powers, like that. Okay, now what? Well, now that we have this equation here, converting this to logarithm gives us what? Well, it gives us log base b of something equals something. Remember, logs solve for the powers. So the power here is m plus n. And that something is the other number we haven't used yet, which in this case is xy. So right away we get log base b of xy, which we're trying to find, is equal to m plus n. But we know m is, let me see if I have a space below. I think I have a little bit of space. Is log base b of x. And n is log base b of y. So there we go, that proves the product rule. And I think I have space to prove the product rule, the power rule over here. So I'm skipping the quotient rule for now because there's kind of something fun you can do. You can actually use the power rule and the product rule to prove the quotient rule, believe it or not. But we'll get to that when we get there. For right now though, let's just prove the power rule. So this proves the product rule. Proving the power rule is something similar. We're going to take, so here we started with the inside of what we're trying to establish, x, y. Here, I want to take x to the r, because that's the inside of what we're trying to establish here. And what is x? Again, x is b to the m. So this is b to the m to the r. And yes, there is an exponent property here. When you have a power to a power, you can multiply the powers. So this is b to the m times r, right? Good. And now what happens when you convert this to logarithmic form? Well, let's see. You get log base, the base is b, of something equals something. Well, logs equal are the power because logs solve for powers. The power in this equation here, if you ignore the middle guy, just this one and this one, the power is mr. Okay, good. It'd probably be best to write this as rm just so we can see the order correct, but m times r is the same as r times m, so I think that's okay. Of what? Of the other number we haven't used, which is x to the r in this case. Base and the exponent we've used, but we haven't used x to the r. And there we go. So now, what's m? M was log base b of x. So this here finishes the proof of the power rule, just like this finished the proof of the product rule. Maybe it's so this this black square here just means I'm done proving basically. So now I don't have space to prove the quotient rule, do I? Well, let me say this. X over y is the same as x times y to the negative 1, and then you can use the product rule and then bring the negative 1 out. It's actually a really nice application of using power and product rule, so just so I can show you that, I'm going to erase this and prove the quotient rule right now. Alright, so this is the proof of the quotient rule, assuming we know power rule and product rule are true. So we want to find out what log base b of x over y is, and what I was saying earlier is that we can write x over y as x times y to the negative 1. Hope we're okay with that. Now using the product rule, which we already established, this is log base b of x plus log base b of y to the negative 1. And now using the power rule, this power negative 1 can be popped out as a multiplier. So this is log base b of x plus negative 1 times this. So in other words, just minus log base b of y. And there we go. It's a pretty short proof. And that completes this. I'll write that box here. But that proves the quotient rule. Now I'm going to erase all of this and do some examples using these rules. So these are two different types of examples that involve solving for x in their logarithmic equations here. And we're going to take advantage of the power and product and quotient rule that we saw in the previous screen. And here, I think it's fairly obvious that the bases are the same in its addition, so I'm going to combine them into a product. So this is log base 6 of 4 times 9. 4 times 9, of course, is 36, so I'm going to replace that with 36 equals x. And there's a few ways of doing this. Remember that log base 6 of 36 is actually a really nice way of doing this. You can convert this to exponential like we usually do. And you can say that this is, well, 6, the base to the power x, equals the other number 36. Since 36 is 6 squared, then you can use one-to-oneness of exponents to say that x is equal to 2. But there's actually a way of doing it using the power rule. Because, of course, we can say, instead of writing this as 36, we can write this as, let me write it like this, x is equal to log base 6 of, instead of 36, let's write it as x squared here in the log. And now what? Now we can use the power rule to bring 2 out. Or, if you remember the properties, the basic properties you saw from 5.2, these cancel out, and you get 2. So right away you get x is equal to 2 anyways. But if you bring the 2 down with the power rule, you'll just have 2 times log base 6 of 6, and log base b of b was 1 using that basic property, which this is kind of a better property, cancellation. But anyways, using the power rule, it's kind of more convincing, I think, that those properties are kind of the same, if you know power rule at least. And there we go. So that's x is equal to 2 for that one. And you can plug it in to check to see that it works. It's actually kind of hard to plug it in because we don't know how to use our calculator to find log base 6 of 4 or log base 6 of 9 yet. We'll learn that soon though. So again, our calculators, at least the one I have, the TI-83, and most calculators for that matter, can only actually calculate log and ln. And that's the common log and the natural log that we saw in 5.2. But what about another base? That's the next big thing we want to talk about in this section. Well, anyways, moving on. I kind of went on a tangent there. Moving on. I'm going to use the quotient rule here in reverse to write this as ln of the first one over the second one is equal to 3. And now what? There's a few ways I could take this. Remember, ln means log base e, so if you want to replace this with log base e, we certainly can do that. And if you want to convert this to exponential, you can write that the base to the power e to the 3 is equal to the inside x plus 1 over x. Cross multiply, move things around and solve for x. There's kind of a nicer way of doing it though. We can actually split this up. Instead of writing x plus 1 over x, we can write it as x over x plus 1 over x. But what's x over x? X over x is just 1. So this is 1 plus 1 over x. So now to get 1 over x by itself, just subtract 1. So we'll get e to the 3 minus 1 is equal to 1 over x. And then reciprocate both sides to get x. So we'll get x is equal to 1 over e to the 3 minus 1. And box that. Perfect. Now you kind of have to be careful sometimes because remember the inside cannot be negative. And since we have insides here being expressions of x, you want to make sure these insides are also not negative. But if you do e to the 3 minus 1 and the reciprocal of that is going to be a positive number. Since e is 2.7, that to the third is going to be pretty large. It's like 20 something, like 24. I forget the number. It doesn't really matter. The point is it's positive. When you subtract 1, it's still positive. Reciprocal, that's still positive. When you add it to 1, it's still positive. And when you just leave it alone, it's still positive. But you have to be careful in general that you can plug your solution back in into your original equation. And if you have a negative inside, it's an extraneous solution right away. So now for some more examples involving the rules we just saw before we move on to the next big theme. And there's two different types of things we can do. We can either expand a logarithm into a bunch of different logarithmic terms, or we can condense a logarithm expression into one log. Now here I want to show that sometimes the parentheses are dropped when it's obvious. So here log base 3 5x means log base 3 of 5x, and log base 3x means log base 3 of x. So very often you won't see the parentheses sometimes when it's not needed, but just keep that in mind. So to expand, what I'm going to do is I'm going to first figure that this is a quotient. So I'm going to write it as, using the quotient rule, log base, the same base, 5 of the top minus log base 5 of the bottom. And now what? Well, now for the first one, we can bring 2 out using the power rule. So that's 2 log base 5 of x. And again, you don't need the parentheses, but I'm going to write them anyways. And here, if you consider log base 5 of y to the second times z to the third, you can use the product rule there, but there's a negative. So technically it would be minus that whole thing. But instead of doing that and then distributing the negative after, I'm going to realize that's going to happen. So they're both going to have negatives. Both of those terms are going to be negative. So in other words, this would be log base 5 of y to the second plus log base 5 of z to the third inside of parentheses, but if you distribute the negative, they both become negative terms. And you don't need those parentheses. And again, using the power rule, this power here comes out, this power here comes out. So our final answer then is 2 log base 5 of x minus 2 log base 5 of y minus log base 5 of z. I forgot the 3. There's a 3 in front, of course. 3 log base 5 of z. There we go. And yeah, if you do this a few times, you'll kind of notice a pattern, and I'll just tell you what the pattern is. Any powers are just in front of those logs with those insides. So notice the one with inside x has a 2 on the outside, the one with y on the inside has a 2 on the outside, and the one with the z on the inside has a 3 on the outside. Also, anything that was in the numerator is a positive term. Anything that was in the denominator is a negative term. And that's basically it. And now here, well, we're going to do the opposite. Instead of expanding it out, we're going to condense it back into one log. So for the first term, there's no power rule needed. But for the second one, there is. 4 can go inside. And you may think, okay, it's subtraction, so use quotient rule. You have to be careful. You cannot use quotient rule or product rule right away, only if there are no numbers in front of the log. Very important. Any number in front of the log, you can bring it as a power first. So apply the power rule first. So you get log base 3 of 5x minus log base 3 of x to the fourth. Now we can use the quotient rule and say that this is log base 3 of 5x over x to the fourth. And yes, there's some cancellation. And now we get log base 3 of 5 over x to the third after canceling. And that's going to be the answer there. Now we're going to move on to the next big property we're going to see in 5.3. So let's take a look. Alright, so now this is what is called the change of base formula for logarithms. I write COB as an acronym for change of base, of course. And here we say log base b of x is equal to log base c of x divided by log base c of b. So basically it's any other base you want and log with that base of the inside over log with that new base of the base, the original base. Now, of course, we get some special cases when c is 10 and when c is e. When c is 10, we get that log base c of x is equal to log base 10 of x divided by log base 10 of b. And this looks a little nicer because remember log base 10, you don't need to write the base. That's just the common log. Okay, good. And our calculators know the common log. So that means we can actually find log base anything just by using quotient of logs. Similarly, when c is e though, we get log base b of x is equal to log base e, which is ln of x over ln of b. And believe it or not, these will be the same, as long as x and b are the same, of course. So you can just take the quotient of the logs or the quotient of ln's, but you can't mix logs and ln's. I want to do some examples here, but before I do that, I kind of want to prove this to you, because of course I like proving things. For the proof, what you can do is you can let log base b of x equal to y, convert this to exponential, and you'll get b to the power y is equal to x. And then the next kind of unobvious step is we can take log base, another base, and in this case it'll be c of both sides. So we'll have log base c of b to the y is equal to log base c of x. Now, why would we do this? Or I guess maybe even better, what do we do next? Well, we can use the power rule. The power rule tells us that we can take y out. So this is y times log base c of b equals log base c of x, and we're home free. Because now all we need to do is divide both sides by log base c of b to get y by itself. The log base c of b's cancel on the left, and we're done with the proof. Perfect. So it's not that difficult to prove, even though it's kind of a not very obvious thing to do. But it's something you can actually always do. Since log is a function, you can take both sides, well, you can take log of both sides, no matter what the base is actually. Anyways, let's move forward and actually apply the change of base formula to see if we can compute these things. Now this one you should be able to do, maybe not in your head, but eventually maybe. But you can at least do this using other means. In fact, if you wanted to call this x and then convert this to exponential, you'll have 4 to the x is equal to 64. You want to write it as a common base. 64 is 4 to the 3, so x is equal to 3. So here you should get 3. Now, I want to apply the change of base formula though. So in your calculator, again, you can only use logs or ln's. Let's just say we use logs here. So in your calculator, type log of 64, close parentheses, divided by log of 4. Press enter, you should get 3. Now again, you can't mix logs and ln's, just stick with one. If you want to use logs, use logs. It's kind of easier to remember. But if you want to use ln's, which I kind of like personally, doesn't really matter though, use both ln's and you'll also get 3, which is kind of crazy. So 2 is a little different though. Why 2 is a little different is because it's not as clean cut. 64 is 4 to the 3, so we can kind of do it without the calculator, or with the calculator if you wanted. Here though, 17 isn't a power of 3. Powers of 3 are, well, 3, 9, 27. So let me just write that out. So 3 to the 1 is 3, 3 to the 2 is 9, and 3 to the 3 is 27. This is the farthest I want to go because somewhere in between 9 and 27 is 17. So 17 is somewhere in between, but it's not obvious what the power is. If you kind of try to use your calculator in some reverse engineering kind of way, you can figure out what the power is to a point. So you can actually say the power is 2 point something, let's say, but it's going to take a while. Instead, if we use this idea of change of base, we can just write this as log of the top, 17, over log of the base, 3. And again, you can also use ln's. ln of 17 over ln of 3 will give you the same thing. Doesn't mean ln and logs are equal. It just means the quotients will give you the same thing provided the insides are the same. And I got with my calculator 2.5789. Now there's more, so that's why I'm writing approximately, because I'm approximating at some point. And I'm just showing as much as I can. On an exam or something, it should like specify round to the nearest so many digits. And if it doesn't, then it's going to be a clean number like 3 was. I should box this, by the way. But in any event, there it is. So if you actually try to take 3 to this power, you won't exactly get 17 because we're rounding, but it'll be really close. So perfect. And now we can move on to some more examples. And let's see those right now. Okay, so here finally I want to show 2 last examples. One will involve the change of base formula. They're both solving problems, of course. And the last one doesn't actually, but it's a really nice scenario where we get into that thing I was talking about earlier, where you may have extraneous solutions, depending on if you plug them in, if you get a negative on the inside. So we'll take a look at that. But first, let's go to this. By the way, this, in my opinion, is a little too much of a complicated example for this section. In fact, really what these examples are doing is kind of building this up for 5.4. Because in 5.4, we'll be taking a look at more extravagant cases like this, or equations like this, and solving. In fact, 5.4, if you're curious, is entitled Solving Logarithmic and Exponential Equations. But enough of that, let's move on. Now, the only way I would know actually how to solve this one, and again, this is kind of a complicated one, is by writing them both with the same power first. Notice, if they had the same base, you can just add their exponents, but the bases aren't the same. So there may be something you can do involving change of base formula right away, but instead, the gut feeling I have is write them with the same power. They're so close. This is x, and that's x minus 1. So if we split the second one up, so 2x stays the same, but splitting this up as 3 to the x times 3 to the negative 1, and notice this makes sense because when you bring these together, it's 3 to the x minus 1 because the powers combine, the powers add, equals 5. Here, there is actually a exponent rule for this. This is just 2 times 3 all to the x. This is kind of like distribution of powers amongst product. Times 3 to the negative 1 equals 5. Now, of course, what this really says is, well, 2 times 3 is 6, so that's 6 to the x. 3 to the negative 1 is really dividing by 3, so this is over 3 is equal to 5. If you multiply by 3, you get 6 to the x is equal to 15, which is 3 times 5, of course. And then if you convert this to logarithmic form, the base is 6, the power is x, so you'll get x is equal to log base 6 of the other number, 15. And then if you want to use your calculator along with change of base, I'll use ln in this case. Let's see what we get. Using my calculator and approximating to 3 decimal places, I got 1.511. Which I think is something that you can kind of figure out that it's definitely going to be bigger than 1. Because 6 to the 1 is 6. 6 to the 2 is 36 already, which is way larger than 15. So 1 point something would be my guess just by looking at it. But exactly what it is this using the calculator. And you can check to see it works by plugging it back in. I'm not going to do that though. And now what? Now onto this one. So here I'm going to use the product rule, of course, to combine these into one log. So condensing them into one log, we get log of, well, x minus 3 multiplied by x equals 1, like that. Distribute this x in, we get x squared minus 3x inside of this log. Log without a base means log base 10, yes. So there should be a 10 there. Converting this to exponential, is, well, the base is 10, the power is 1 because log solve for powers. So 10 to the 1 is just 10 equals x squared minus 3x, and what we have on our hands here is, yes, a quadratic equation. So now we can subtract 10 to the other side, so the 0 is on one side. And we can attempt to factor this, and I believe this actually does factor as, let's see. Hope that shows up, perfect. So two numbers that multiply to 10 and have a difference of 3 are 5 and 2. And in order for the signs to work out, they need to add to negative 3, so the larger one must be negative. 5 and 2 is what I meant to say. There we go. And this works. Negative 5 times positive 2 is negative 10. Negative 5 plus 2 is negative 3. If we FOIL it out, you will see that it also works as well. And finally, using the zero factor property, we get x is equal to positive 5 or negative 2. There's an issue. When you plug in 5, there are no negatives. It's positive and it actually works out. 5 minus 3 is positive 2, so we're good. And then 5 is still positive, so we're good. Negative 2 doesn't check out because negative 2 minus 3 is negative 5. Right away, extraneous. You can't have a negative inside of a log. Its domain is only positive numbers that are non-zero. Similarly here, we don't even need to check this. Once you have one of them negative, right away it's extraneous. But yes, it also fails this one. Log of negative 2 is log of a negative. That's an extraneous solution, so right away x is equal to 5 is our only solution, and there we go. So that actually concludes 5.3, and I'll see you in the next video for 5.4, and we'll see how crazy it gets. See you then. Thanks for watching.